So good afternoon, everybody. I'll be talking here about Pytorch Inferno. This is a Python package that I recently released, designed to be kind of as close as you can get to a drop-in implementation of the Inferno algorithm. Now, to begin by hiding that. Now, what's going on here? It's decided to cut off the bottom of the slides. Well, that's annoying. I'll go through it normally. Possibly increase the resolution. Okay, hopefully that's readable. It worked 5 minutes ago, but it doesn't anymore. Okay, so if you imagine just a common, your typical high energy physics search, you're going to do all your event selection, get to the end, train a binary classifier to separate your signal from the background. The loss here is binary cross entropy. You're completely ignoring any systematic uncertainties that you may have on your input features or the normalization of the processes you're considering. You get to the end, you get a very nice separation between signal and background. You bin it and you use it as a summary statistic in order to perform a statistical inference of your final parameter of interest, your signal strength. And it's only now that you begin to consider that you may have systematic uncertainties on your data. Now, if the effect is large, then it's actually going to worsen your sensitivity to the signal, and you're getting worse performance than you might otherwise be able to get. So the Inferno algorithm that was published in 2018 by Pablo de Castro and Tommaso Dorigo. Here you're actually considering the systematic uncertainties during the training of your model. It allows you to directly optimize a deep neural network for statistical inference of the parameter of interest. And the loss here is actually one of the elements of the inverse of the Hessian of the log likelihood with respect to the parameters in your model, your statistical model. Basically, you encourage it to have a steep gradient with respect to your parameter of interest and a shallow gradient with respect to the nuisances. So here's the profile log likelihood of your parameter of interest. If you make this more steep, you get a more you reduce the uncertainty on your inference. And similarly, if you flatten it out with respect to your nuisance parameters, you learn to become more resilient to them. Now, the output of Inferno is already a pre-binned summary statistic. So you have a softmax on the output, and you kind of learn these unordered classes, and they emerge as a function of the training. And this learned binning also then allows Inferno to account for nuisances on the normalization of the processes as well. I'll discuss the algorithm a bit further in a few blog posts that I've linked to here. Now, when you actually come to implement Inferno, you first of all begin by showing the data how it could be modeled, how it could be modified by systematics on the inputs. And then you pass this modified data through the deep neural network. You then, inside the loss function, compute the signal and background shapes, normalize them, and then compute the profile log likelihoods. Differentiate it with respect to the nuisances and the parameter of interest. And then the actual loss that you use is one of the elements of the inverted Hessian. And you backpropagate this as normal through your network and update the parameters. Now, a few of the difficulties here are that the data needs to be modified before it gets passed through the network in order to include the effects of the nuisances. And depending on your framework, you may also then need to reevaluate the model response on data that doesn't include the nuisances to get the Asimov response, the default response with no nuisances. So the aim of Pytorch Inferno is to try and provide a drop-in implementation of the loss, such that you don't have to go in and start modifying the code that you've written for the training loop. And so you can also then interchange it easily with other loss functions to compare the performance. So I chose to implement it as a callback class. If you're perhaps familiar with Keras, you'll know that callbacks are a way to modify the model, the training, the data, aspects of the training without having to modify hard code. Yeah, and they can perform these actions at several sort of interjection points during the optimization cycle. So the Pytorch Inferno package provides a basic training wrapper for Pytorch and quite an extensive callback system, plus all the basic inference system that you need in order to do negative log likelihood minimization in the presence of nuisance parameters. Now, actually including Inferno in your analyses, it's going to depend on your analysis, the nuisances that you have, the processes, the signals. So the best we can do is to provide an abstract implementation for Inferno. The user can then inherit from this and override the required functions specific to their task. Yeah, I've tested the package and it successfully reproduced the paper results on the toy dataset. Now I'll skip through these cells quite quickly. You can go back and read them. Here I'm just showing that yes, the callbacks can interject at the required points during the optimization loop. The data can be modified. So this is one of the main methods you need to override the org data. You take the input data, you can mask it if you want to select signal or background. You can mask to select individual features, and then you show how it would be modified by the systematic, these alphas. Alphas here, they're all at 0, they're nominal values, so you're not strictly modifying the data. All you're doing is showing if the systematic changes, how do the inputs change? And then you compute your loss. So inside the loss computation, you compute the signal and the background shapes. And then you go through and you do you construct your log likelihood. Yeah, find the Hessian of it, invert it, and then return the required element of it. So just to see this all in action, we'll look at the paper example. This is just a 3-feature classification problem with nuisances affecting the position and the scale of 2 features and the normalization of the background. So there's a method here to import the data that's included in the package. We define the DNN. This is just a typical deep neural network in Pytorch. We have this softmax on the output and 10 outputs. This is the 10 bins in our final summary statistic. And then we put this into a model wrapper to handle the training, the saving, predicting, and whatnot. Now for Inferno, we set the loss to none because we're going to use this paper Inferno callback. We have some constraints on our nuisances here, so we can say that we know from previous experiments that the normalization is a Gaussian centered, centered to 0 with a width of 100, maybe 100 events. We train it. Now for binary cross entropy, all we need to do is just change the model to be a sigmoid single output. Tell it to use binary cross entropy, and then we cut out Inferno. And then we can train that as well. There's a bit of code here, so I'll just skip over. Basically what we do is we compute the profile log likelihood, and we can see that both of them predict the signal strength of 50. However, because Inferno was trained to become resilient to the nuisance parameters and was made aware of them during the training, its final precision on the parameter of interest is much, much lower than what we get from binary cross entropy. So just to summarize, yeah, the Pytorch Inferno package provides a starting point for using Inferno in your own analyses. It's all pip installable, so it's quite quick to try out. As I mentioned earlier, due to the task-specific nature of Inferno, it's kind of difficult to avoid the user not having to inherit and build their own classes. There is an approximation that I haven't discussed here that perhaps could be generalized to work directly on the systematic data sets that you get in a typical HEP analysis. Yeah, and if you don't like PyTorch, the code kind of shows how you can potentially implement it yourself for your own chosen framework. And there's also TensorFlow 1 and TensorFlow 2 implementations of Inferno, so I've linked to that. So thanks very much. I'm afraid I've gone a bit over time. I don't see any questions.
Okay, thanks very much. Sorry. A quick one maybe from my side, interactively. You mentioned these other implementations, but for example, you may have heard earlier today from PyHEP that they have different backends. So is this a possible route that instead of having a completely different package, we actually would have different possibilities of using the same algorithm, with the same implementation, but then you could use PyTorch if you feel like it, or
yeah, so potentially. Okay, so there's this a group, Grad HEP. We were meeting a few months ago, and we discussed the possibility, because there's a lot of very similar algorithms. Inferno, Neos. I can't remember the name of it, but or the author actually. But there's a third package, and they all basically do the same thing, but just have different slight changes. So we're thinking that kind of the holy grail would be to have a single package that implements all of these algorithms, and the user is free to say, okay, I want to do histogramming, I want to do KDE for the summary statistic. I want to do this. I want to compute the likelihood, or I want to do I can't remember the name of the technique now, pointwise differentiation. Anyway, yeah, basically a single package that does all of these. And I think at that point, once we've all sort of individually worked out how all these subsystems connect together, then maybe we could go with something that is kind of framework agnostic. I think that'd be really cool. Because yeah, I guess at the moment everyone's basically split between TensorFlow, PyTorch, JAX. So it'd be nice to have a single repo that did everything.